Hello, welcome and an excellent evening, and today I want to talk a little bit about memory on the IBM PC and compatibles, as well as pointers, because I got a question on one of my last videos where that person said, I'm lost at the part when you use pointers. Could you please elaborate a little bit next time when, how and why you are using them? Thanks. Usually I answer these questions under the video and say I'll put it on my list, and my backlog for topics is extremely long because those questions are often very specific on certain topics that take a lot of time to prepare and are not very general. However, as this series here, Let's Code MS-DOS, has been running for quite some time, I thought it might be necessary to do a few refreshers for people who just joined us like a couple of episodes ago or something, or want to join us just seeing this very new video, or at the time of release very new video. So it might make sense to go back and see how IBM PCs used to handle the memory in the so-called real mode and with the limitation of 1 megabyte at maximum, and how pointers actually work, because some languages hide away pointers, for example basic, Java, or some Lisp variants. There you will never see any pointers. But if you go to languages like Pascal under DOS, or Turbo C here, or any C variant actually, you will have to deal with pointers. And the question is, what are pointers? How are they used? When are they used? And so let's talk a little bit about that. Here is a little memory map of the IBM PC from -0degrees.net, which is a great resource for everything IBM PC. And it only shows the upper 384 kilobytes, because the lower 640 kilobytes is not super interesting, because that's actually mostly free. There will be some parts of DOS in there and some system variables basically, but most of that 640 kilobytes is just free for usage. The original IBM PC and XT were using a CPU called the 8088, which could only address up to 1 megabyte of memory in one go, easily at least. And the upper 384 kilobytes that you had was also already used by certain things, for example video RAM, depending on which card you had, BIOS expansions, and the motherboard BIOS, including BASIC on the IBM PCs. So that's something that you should know. And you also see that the address here is written in an interesting fashion, like F8000. And this actually not quite how addresses work if you're programming under MS-DOS, because the 8088 and 8086 use something called segmented memory addressing. The predecessor of the 8080, and also its clone the Z80, and similar machines like the 6502 based computers like the C64, PET, VIC-20, etc., they were using basically a flat memory model with only 16 bits of address space, which gives you access to only 64 kilobytes. Building larger address lines would mean that you have to build logic that can support wider numbers than 16 bits. Intel didn't want to do that because it would have been expensive at the time, used a lot of transistors. So what they did was to invent this, or probably not invented, but use the segmented addressing. You would have some segment address and some offset into that segment. Every segment address is divisible by 16. So every 16 bytes a new segment starts, and it's 16 bytes long. So every segment is exactly 64 kilobytes, just as it was on the 8080 and the Z80. The offset is also 16 bits long, so as I said, you can point into that segment any way you like. Since every 16 bytes you get a new segment, you can in total address 16 times 65,536 bytes. That is exactly 1 megabyte. So it's a bit annoying to deal with this, especially on a machine code level. You have to rethink a little bit how all this works. Later processors like the 286 and especially the 386 introduce different memory addressing modes, with the 386 having kind of flat addressing again with 32-bit pointers. But that's not a topic of this video. Maybe we'll touch on that at some point in the future, but here I just want to make sure that you know that there are segments and offsets which are currently invisible to you in C, but they will become visible in Turbo C once you need to address a certain amount of memory. That being said, let's get back to the pointers. I've written down a very simple program here that doesn't require any pointers. We have a function called sum that takes two integers and calculates the sum of those integers and returns that. The main program will initialize two variables called a and b, clear the screen, and then print out a plus b equals, and then calls the sum function. So we would expect there to be an output of a plus b equals 3, and then waits for key press. Let's run this, and indeed we get a plus b equals 3. Now, what if we wanted to pass an arbitrary number of integers, let's say? How could we do that? We could do that by passing a vector or an array and a number, how long that array is, and we could, for example, then write a loop. Let's do that here. We need a running variable here, a loop variable, and we'll do something like I equals 0, I is smaller than n, we increment I, and then we will do something like, what else do we need? We need a sum variable, which is this here. We'll initialize that with 0, and we'll do s plus equals a of I, and then we'll return the sum. Let's do this here as well. So a is some kind of vector, and it contains 1, 2, 3, let's say. Sum of a, let's say, and this here takes currently 3 entries, so I'll just write it like this, and the sum is 6. Okay, cool. Now, where are the pointers, you might ask? Actually, we are already using pointers, but they are currently invisible because every array in C is actually also a pointer. This notation here, a square brackets, means this is a pointer to a certain number of elements of type int. We could have also passed this to a function which doesn't have this signature, which says I'm taking an array of ints. We could have also said I'm taking a pointer to integers and a certain number n. This will actually work exactly the same way, even with this subscript method here of square brackets. It will still use this information, and we can prove this by running this. We again get 6, there's no compile error. So what does this actually mean? The star, if used with a type in C, means this is a pointer instead of the usual type. You could also format it this way. Some people like this better. It means this is a pointer to an integer. What is a pointer? A pointer is simply a memory address. So we already know that an address in Turbo C, for example, contains a segment part and an offset part. We can actually print it out and see where this thing lives by using the printer function, and we can write segment and offset equals percent, let's take, I think %x should be hexadecimal, %x, and then a \n. And there's a function called fp segment of A and fp offset of A. This will give us the segment and offset parts. You can look that up in the help file. It should be in the DOS header, which I included above, and there are the two functions, or actually they're macros, fp segment and fp offset. Ignore the far pointer here, and we will probably also get a warning. Oh, we don't. That's nice. We can run this. And this will output the actual segment and offset values, which depend on how large the memory is when it is launched. For example, now we have 5522 FFD4. Let's see if it's the same when we run this program directly from DOS. And indeed it changes because TurboC is not loaded. The offset is still the same because the program is always loaded into a certain segment, but at the same offset. So the offset will always be FFD4 for this special variable, but the segment changes because now TurboC is not a memory and we can load into a lower segment. Let's open this again. And just to prove it, if we run it again, we again have 551A and FFD4. Okay, so indeed arrays are pointers and we can use them interchangeably, in most cases at least, and they basically contain an address to one or more objects. They are basically just pointing into the memory map somewhere down here below the 640K line and are basically the house number of a memory cell. Now, why do we want to do that? The thing is, this is very useful for variable length data. Here we have still a fixed number like 3, but imagine that you read in a data file and want to compute the sum of a lot of lines, or maybe the average or something, and you don't know in advance how many those will be. You can't write a function having like 10, 15 or 1,000 arguments. That wouldn't work very well. So instead, you can use pointers and allocate a flexible amount of memory and fill that with your data and pass it around. That's exactly what we'll do now. So what if we were to make this dynamic, basically? Then we would actually convert this also into a pointer, and we would need to allocate actually some memory, because right now this pointer here points to some random value. We could initialize this with the so-called null pointer, which is an invalid pointer, or there would be just some random garbage in here. So instead what we'll do is the following. We will pick a random number. I don't know, let's say we are going to use 123 different numbers. Those are definitely too large to pass them individually into this function. We would need to allocate memory for this, because right now we don't have any memory space here. And you do that by using the standard C function called malloc. And we can also have a look here in mem.h. There should be, oh no, sorry, that should be the standard lib, I think. There should be a function called malloc. It takes a size argument and returns a pointer to void, which is basically a pointer to not a specific type, but to a number of bytes. And yeah, that can automatically be converted into a pointer of integers. So we want to allocate 123 integers, and we do that by writing 123 times, and then there's a built-in function or operator called sizeof integer, and this will return the number of bytes on this platform that an integer takes. On DOS and TurboC this will be 2 bytes, so it will allocate 246 bytes. This will be done like so, and we will also need another run variable, and we will fill this with numbers. So we will do something like for e equals 0, I smaller than n, and we could actually use n here to make it more pronounced, and we will fill the element with the number itself. Let's say something like that. This way we actually use a pointer that was initialized with a null pointer, which would crash the computer or the runtime system if we were to try to access it. And then we allocate the memory, initialize every memory cell in there with a useful number, and then calculate the sum. Let's have a look. And there is our new memory, and it's now the sum is 7,503, which is probably correct. However, we are now leaking memory. The amount of memory that is available to DOS will be less than before, perhaps. Might be, I'm not sure if the memory is freed, but at the end of using something and before you quit the program, you're supposed to return the memory by using the function free. So if we look again at the standard library, there should also be a free function that takes a pointer to the allocated block, and it doesn't return anything, and it will free the memory that was allocated using the malloc function. So this here will be a little bit more of a correct program. Still it produces the same output. So those are very simple ways on how to use pointers. However, as you've seen, there's more to that with the segments and offsets. And in TurboC, you can find different options for memory models. Currently, we are compiling for the memory model small. If you press F1 here, you will get a help about all the different memory models. There's 6 different models: tiny, small, medium, compact, large, and huge. And as the name suggests, they are for programs that have different memory requirements. The smallest one is called tiny. And this model has a total of 64K for all the code, data, and stack in your program. All functions and data pointers are near by default. Tiny model programs can be converted to .com format. Instead of .exe files, you can convert them to .com files, which might be useful for certain things. They mentioned pointers are near. Let's have a look at one of the other models. Let's say the large model. This model has up to 1 megabyte for code, 64 kilobyte for stack and static data, and up to 1 megabyte for the heap. Heap is everything that we allocate via malloc. And all functions and data pointers are far by default. Okay, that sounds interesting. What are near and far pointers? We can actually force the pointer to be near or far in TurboC. We can't do that in regular ANSI C. If you're coding in Linux, for example, with GCC or CLang, you won't be able to do that. This is something specific to DOS C compilers. For example, I can have 2 pointers called near pointer and far pointer maybe. And we can now add another keyword near and far to this. We have now created 2 pointers called near pointer and far pointer with the extra keywords near and far, and they declare those pointers to be near or far actually. So what's the difference? The near pointers will be smaller. They will only have an offset and will be using the current data segment that the program has for these variables. So there will be only an offset, let's say 16-bit offset. And a far pointer It's actually pointing to further away segments, and this will be a segment offset style pointer. So in theory, we should actually be able to see a difference here if we were to do something like this. Let's write near colon %d far colon %d and then \n and do something like size of int near star and size of int far star. And we'll get to why this is actually worthwhile. And here we can see it. A near pointer consumes 2 bytes of memory and a far pointer consumes 4 bytes of memory. So the idea here is very simple. If you know that you will be using stuff in the current data segment, that you don't require malloc that is going beyond the 64 kilobytes of your current segment that you're working in, then a near pointer is sufficient, and you will save space on memory, obviously, because if you have multiple pointers in a more complex data structure, this will be half as expensive as a far pointer. On such old machines, that actually makes a difference. Plus, taking the address basically, or taking the contents of this address might also be faster due to the way that the machine code works, if the opcodes are, for example, smaller. So that is the difference between the near and far pointers. There's actually a function also in one of the header files in alloc.h. There are specific functions. Malloc will probably default to whatever your memory model says. So typically for tiny and small, that it might return a near pointer, but you can force it to actually produce a far pointer by using the far malloc function, which, as you can see, returns a void pointer, a void far pointer. So that definitely should work out just as expected. Let's try to do that. Let's do a near pointer. And we need to add this at the top here, include alloc.h. And we can do a regular malloc perhaps of, I don't know, 100 bytes. And we can do another malloc, a far malloc of also 100 bytes. And then we can try to print the address of those. So we will use the same thing that we had before. Near pointer equals %x. Let's see if what the segment here returns. Let's do fp_seg of near pointer and fp_seg of far pointer. And you might ask, of near pointer obviously, you might ask if it only contains an offset, what's returned here? So probably it will return the address of the data segment, of which might be the code segment here or a different segment depending on the memory model. But that should work. There will be one warning because we didn't use far pointer variable yet. So we will do that as well. I'm gonna put in a couple of new lines here to make it a little bit more readable. We'll do the same for the far pointer variable. And we'll have to also release the memory. We have a far free, which takes a far pointer, and of course the regular free. So we'll do that here, far free far pointer, and also free near pointer, just so that it works out well. There are no errors, no warnings, and there you see it. Near pointer is 55 EE and offset is also 55 EE, which is interesting. So it seems that the segment and offset are the same here, or did I miswrite? I did miswrite. I was just copying myself, which we'll also do here. That should work out fine. This is much more sensible. 55F0546. So this seems to be the default data segment in the small memory model here, and this seems to be one of the far segments basically. As you can see, it's exactly 1000 hexadecimal further away than the near pointer. We can also try and put something here on the stack basically, or we already have. For example, we have n here, which is an int, so we can try and print out the segment and offset of the variable n. And how can we do that? We can convert this into a pointer by taking the address of it, which you do with the ampersand operator. So this will give us also a pointer to int, and especially to this variable here. And variables that are declared inside a function, such as main, will not reside in a far segment, but on the stack segment. So let's see what the stack segment looks like. And you can see it's actually the same as the one for the near variables. We have 55F2 as the segment for the near pointer that we allocated using malloc, and 55F2 as well for the local variable that resides on the stack. But you can see that the offset here is 550, so it seems that probably the first couple hundred bytes is code, and after that are the malloc variables inside this little segment. And the stack grows from the top, so from FFFF, and there are a couple of things on the stack already. But here at FFD8, we suddenly have the variable n. So that's how all these things function. And I think that is already almost everything you need to know. The question is, why would you use stuff like that? Well, it gets even more interesting once you have structures which are more complex data types. You can have something like a structure. Let's say we call it player or something, which has perhaps some variables x and y for position, something like position x, position y, an integer for health, etc., etc. Structures like those cannot be passed around in a regular fashion. Like if you would like to draw the player character, you can't write something like player p or something. What you would actually have to write, struct player p actually in C, you would have to write star p. You have to pass a pointer, because C will only copy things into a function when they are primitive data types like int or float or char or something like that. More complex types like arrays get passed around as a pointer, as you've seen here in the sum function, which you can actually still write as this, right? So this is the very same thing. I'm gonna disable this for now because this is not complete code. This should also work just fine. There's no error here. So if you were to have more complex things like vectors, arrays, or structures, then you need to use pointers to pass these things around. And yeah, that's, I think, the most important stuff that you need to know about pointers. The very important thing is that you have to keep track of when you allocate something and when you free something, otherwise you will have memory leaks, and over time the memory will fill up and no free memory space will be left, and your program will get errors, because once there is no more possible stuff to be mallocked, then malloc will return null pointers and your program or computer will crash. So that's for you to keep in mind. C is a very low level language compared to other more modern languages. So you have to keep track of this yourself, basically. Okay, I think that should suffice for you to have a small refresher on how DOS memory management works in real mode, what we are doing here in Let's Code C on MS-DOS. So I hope you enjoyed this, you learned something, and make sure to like, share, and subscribe, the usual stuff. Leave a comment if there are more questions. As I said, very specific questions will probably not answered in any reasonable time, but I take these as ideas with me and write them down. More general things where I see, okay, we need to have another refresher, I might do that in a couple of episodes. But that's it for today. As usual, all the links for supporting me are in the video description, and yeah, see you in the next one.